Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's activity is a brief tour of the motor family tree. Our objective is to recognize identifiable traits that distinguish one motor from another and introduce basic concepts and terms to assist you in the task of classifying motors when encountered in their natural habitat. Right up front, I'm issuing a correction about the title of this lecture and the family tree it's referring to. It would be more appropriate to call this the rotating electrical machine family tree, where the broader title pays homage to the dual nature of rotating electrical machines, motors on one side and generators on the other. The reason I'm sticking with the motor title, though, is the same reason beer companies use girls in bikinis to sell beer, and not the actual red-eyed and bleary clientele that drink it. It's sexier and more likely to attract interest. You should be aware that the family tree I'm describing can be easily extended into the generator realm with very little difficulty. For example, there are three-phase AC synchronous motors and three-phase AC synchronous generators, with very little conceptual difference between them besides that of direction. Motors convert electrical power into rotational mechanical power. In contrast, generators convert rotational mechanical power into electrical power. It's really that simple. There are subtle and not so subtle differences between the two machines designed exclusively for one task and not the other, but for the most part, a high-level discussion like this can encompass both aspects. Staying with the motor designation, however, we could say we're talking about a type of actuator, where the term actuator is a blanket-level term meaning a device that can take one form of input and transform it into mechanical output. Actuators are things that move. We could parse the whole actuator designation up using several different perspectives. For example, what is the type of input power? Hydraulic, pneumatic, electrical, etc. We could also divide those actuators into the type of mechanical output they produce. For example, linear, rotational, or oscillation, which is a form of partial rotation. A hydraulic cylinder is a classic example of an actuator that translates hydraulic power into linear mechanical power. The hydraulics playlist, available at the Big Bad Tech channel, deals extensively with hydraulic cylinders and hydraulic systems. A motor is a classical example of an actuator that converts electrical power into rotational mechanical power. Rotating mechanical power, as we'll learn in later lectures, is characterized by two measurable quantities: a twisting force known as torque, measured in units of Newton meters, and rotational speed, measured in revolutions per minute, or RPM. Mechanical power, in units of watts, is the product of torque and rotational speed divided by the constant 9.55. Keep in mind, additional mechanical linkages and accessory components can modify the style of mechanical output. For example, a linearly actuating hydraulic cylinder could tip or tilt a load using a pivoting trunnion and/or clevis mount, or a rotating electrical motor could drive a conveyor belt in a straight line using a belt and pulley. The branch of the actuator family tree we'll be talking about today consumes electrical power and produces rotational mechanical power. This is my definition of a motor. Regardless of the later subdivisions within the motor family tree, every one of the devices we'll be discussing today does exactly that, the only distinction between them being construction. Think of this lecture as an introductory field guide to motors with an emphasis on the term introductory. Far more motors exist than this initial walkthrough suggests. In the interest of brevity, I will purposely ignore and intentionally neglect odd motors, special motors, weird motors, and motors I straight up don't like. The motors as presented in this lecture are devices you will most likely encounter on a regular basis. The first question any aspiring technician may ask is, what do motors look like? Externally, a motor has a body, a shaft, and electrical connections. The body could be little, big, red, blue, roughly cylindrical, or maybe even pancake-shaped, but normally the body is the large part that doesn't move and is normally attached to something big like a frame or a floor. The shaft is the moving part, and it is attached to a load that needs to be turned. Most of the time there's a flat, a key, or a keyway in the shaft to directly couple the shaft to the load, a coupling, or perhaps a gear or gear set to increase torque and decrease speed, or the other way around. A coupling compensates for misalignment of the shaft with the load and enables a technician to take the pair apart for repair and service. The gearbox and coupling actually aren't part of the motor, but they're essential for the motor to properly do its job. The next best question an aspiring technician may ask is, what do motors eat? A motor consumes electrical power as its input, so it stands to conjecture there might be motors that prefer AC and those that prefer DC. This is the most prominent split in the motor family tree. Additionally, we can divide AC into two branches: industrial three-phase AC motors and residential single-phase AC motors. We've now divided our family tree into three distinct branches, and there is very little crosstalk between them. with one exception being the universal motor, which as the name implies can run off DC or single-phase AC. It doesn't do either task particularly well, but it does do both tasks. Let's introduce some basic motor terminology. If being an electromechanical technician was easy, everyone would be an electromechanical technician, so we've got to throw a couple impediments in the way of those studying this topic by making the terminology as confusing as possible. The first hurdle is what the different branches of the DC-AC split call the rotating parts and the stationary part of the motor. On the AC side, it's pretty easy. The rotor is the rotating part, and the stator is the stationary part. Get it? The rotor rotates, and the stator is stationary. On the DC side, the armature is the rotating part, and the field winding is the stationary part. If you use the term armature to describe the rotor on an AC machine, or rotor to describe the armature on a DC machine, people will most likely understand what you intend, but it's generally not considered good form to do so. Customarily, most individuals start with DC motors and work their way up to three-phase AC motors. This is the wrong way to do this. I prefer beginning our discussion of motors inside the three-phase AC motor branch for a rather compelling reason. The reason being, people will pay you good money to work on three-phase AC motors. One of the most popular motors on Earth is the three-phase AC squirrel cage induction motor. If there is a single subject you can direct your attention towards, let it be the three-phase AC squirrel cage induction motor to the exclusion of all else. Keep in mind, I'm tailoring this lecture series towards students that regularly gain employment in power generation and transmission, including solar, wind and hydro, advanced manufacturing, instrumentation process control, and industrial maintenance. If your interest is very specific, feel free to skip around. Starting within the three-phase AC motor branch presents some unique challenges. They're not the easiest motors to understand, and it would be preferable that individuals have a requisite knowledge of three-phase AC circuit analysis. This isn't always the case, and if you just blew in from some random corner of the internet, just stick with me for a moment, because this lecture is meant to be a familiarization only and doesn't go into a lot of technical detail. The three-phase AC side of the motor family tree, of which there are two sub-branches, three-phase AC synchronous motors and three-phase AC induction motors, is characterized by a rotating magnetic field on the stator. Later lectures will discuss the rotating magnetic field phenomenon in greater detail. Long story short, three voltage waveforms with identical magnitude and frequency, yet phase shifted from each other by a relative 120 degrees, cyclically excite the stator windings such that a smoothly rotating magnetic field revolves inside the stator and the rotor responds to it by rotating in a similar direction. First L1 peaks, then L2, then L3 in a continuous circle. In addition to being easier to generate and transmit, the ability to create a rotating magnetic field is perhaps three-phase AC's greatest advantage and largely the reason three-phase AC is employed in industrial settings. Certain types of single-phase AC and DC motors do use a rotating magnetic field, however they have to resort to some undignified trickery to do so. Another advantage of three-phase AC is that the direction of the rotating magnetic field, and thus the rotational direction of the rotor, is capable of being reversed simply by interchanging any two stator leads inside a three-phase AC system. For example, application of L1, L2, L3 in this fashion might see the motor initiate rotation in the counterclockwise direction. If, however, we swapped which windings experience L1 and L2, we'd see the motor initiate rotation in the clockwise direction. Lastly, three-phase AC motors make it possible to create large motors, where the term large is a somewhat arbitrary line. Try lifting a lock gate on a dam with a single-phase AC motor. It's not going to happen. Industrial three-phase AC, not a problem. Since both synchronous and induction-style three-phase AC motors use a rotating magnetic field in the stator, let's discuss some properties of the rotating magnetic field before we compare and contrast the two types. The speed of the rotating magnetic field produced by the stator is known as the synchronous speed. Synchronous speed can be calculated as taking 120 times the excitation frequency divided by the number of poles per phase, or as I prefer, 60 times the excitation frequency divided by the number of pole pairs per phase, since the north must accompany a south and vice versa. Note the distinction between the two formulas and my overly dramatic pronunciation, the number of poles per phase and the number of pole pairs per phase. Long story short, lower frequency means a slower synchronous speed. Higher frequency means a faster synchronous speed. Conversely, a lower number of pole pairs per phase means a faster synchronous speed, and a higher number of pole pairs per phase means a slower synchronous speed. A type of modern power electronics device, known as a motor drive, can be used to directly decrease or increase excitation frequency and thus change rotational speed of a motor under its direction with a fixed number of pole pairs. We'll examine motor drives in greater detail in later lectures. The functional division I'm drawing between synchronous and the induction split in the three-phase AC motor branch is based on performance with respect to the synchronous speed. As the name implies, the rotor speed of a synchronous motor matches, follows, or is otherwise synchronized or locked in step with that of the stator rotating magnetic field, whereas the rotor speed of an induction motor is not. The rotor of an induction motor must by necessity slightly lag behind the synchronous speed for them to function at all, even in the no-loaded condition. It is for this reason induction motors are sometimes called asynchronous motors, meaning not synchronized. I say again, the rotor of a synchronous motor is synchronized with the stator rotating magnetic field, whereas the rotor of an induction motor is not. The rotor of an induction motor must by necessity lag behind the synchronous speed for them to function at all. This is to suggest that synchronous motors are constant speed motors, whereas we might expect the rotor speed of an induction motor to vary as a function of applied torque. Long story short, less oppositional torque, an induction motor will speed up, more oppositional torque, and an induction motor will slow down. Let's compare and contrast the two basic types of synchronous motors: electrically excited synchronous motors and permanent magnet synchronous motors. Both these motors make use of a rotating magnetic field on the stator, and inside their operational range, we should expect the rotor speed to remain synchronized or to perfectly match the synchronous speed of the stator. Both of these types of synchronous motors feature a magnet on the rotor, the principal difference being how that magnet is established. As implied by their titles, an electrically excited synchronous motor necessitates an electrical connection to the rotor for the purposes of establishing an electromagnet, whereas a permanent magnet synchronous motor really does have a permanent magnet on the rotor and necessitates no additional accessory electrical connections. These differing means of rotor construction present some advantages and disadvantages. An electrically excited synchronous motor features a coil of wire on the rotor core called the field between F1 and F2. When the field is energized by a DC source known as a DC exciter, it establishes an electromagnet on the rotor. We'll examine the theory behind electromagnets in the electromagnetic interaction lecture. As a summary of the process, the strength of the resultant magnetic field is proportional to the current flowing through the coil, and the polarity of the resultant magnetic field is dependent upon the direction of current flow. More current means more magnet, less current means less magnet. Once established, the rotor electromagnet simply locks in with the stator rotating magnetic field and follows it around and around, matching the synchronous speed. The schematic symbol for an electrically excited synchronous motor shows 3 connections to the stator reserved for three-phase AC, and 2 connections to the rotor reserved for the DC exciter. For the purposes of this lecture, we're presuming the DC exciter is an external voltage source. However, be aware other methods exist, including those exciters mounted on the rotor. Getting DC electricity from a stationary external DC exciter to a rotating rotor presents us with a structural challenge. How does one send electricity using 2 wires to something that revolves 360 degrees without twisting the wires into a knot? The device that allows one to do so is known as a slip ring. A slip ring is a means of electrical connection between a rotating and stationary member. There are several different forms of slip rings, but the most basic configuration takes the form of conductive rings in the rotor shaft which provide electrical contact to the rotor coil. Stationary conductive brushes held in place by a spring and brush holder ride along the conductive rings, such that the coil on the rotor maintains constant electrical contact with the stationary electrical inputs regardless of orientation. Here an ohmmeter indicates connectivity is maintained from the stationary electrical connections through the rotor field windings regardless of the position of the rotor, thanks to the brushes and slip rings. Slip rings are not maintenance-free by any means. The brush itself is a consumable, and at a certain point it will wear out and cease to function. A large portion of low-level maintenance performed on electrically excited synchronous motors and generators is simply replacing brushes and cleaning out brush dust. A permanent magnet synchronous motor solves this maintenance problem by installing a genuine permanent magnet on the rotor. You'll note the schematic symbol for a permanent magnet synchronous motor includes only the 3 three-phase AC connections to the stator and no connections to the rotor. This alleviates the necessity of slip rings, but comes at a price. Namely, you can't turn a permanent magnet off nor change its strength. That kind of comes with the whole idea of permanence. You'd think a permanent magnet on the rotor would be the single best technological innovation since they replaced the turd brown M&M with a blue one, but this isn't always the case. One of the principal advantages of electrically excited synchronous motors is that the rotor electromagnet can be turned off or on at will and increased or decreased in strength. As an especially cool application of this feature, consider something known as a synchronous condenser, which is neither a motor nor a generator, but rather a customizable power factor correction device. A synchronous condenser is for all intents and purposes an unloaded electrically excited synchronous motor, and by increasing or decreasing the exciter current, a synchronous condenser can balance reactive power requirements from a larger system at the point of use. You recall, power factor corrected systems draw less source current and as a result are more efficient in terms of transmission and distribution. We'll examine synchronous condensers in greater detail in later lectures. Theoretically, synchronous motors, regardless of construction, can be expected to maintain synchronous speed regardless of applied load inside its operational range. These devices are not magic though, and they do have practical limits only under which they can perform as advertised. Pull-out torque is the point at which a synchronous motor is so loaded that it pulls out of synchronization. You'll immediately be aware of this event because of the change in speed, torque, and electrical characteristics, horrendous noise, and your lab instructor's boot planted firmly in your butt telling you to shut her down. Experimental verification labs may ask you to determine the pull-out torque for a synchronous motor, but realize this is not something you want to do on a regular basis. Pull-out torque is roughly linear, dependent upon field strength, although there are practical limits to this relationship, and at the upper limits of field excitation, we might expect the rotor electromagnet to reach saturation whereby pull-out torque starts to flatline. Lastly, synchronous motors often necessitate more complicated starting circuits and protection schemes than would a similarly rated induction motor. One of the principal issues related to starting a synchronous motor is that upon closure of a full voltage starter, the stator rotating magnetic field is instantly established at full speed, whereas the rotor in applied load with some level of static inertia may take some time to come up to this speed. The analogy I like to use about starting a synchronous motor is having your buddy invite you to go water skiing, only passing the dock at 60 miles per hour and just tossing you a rope. It's going to rip your balls right out of your sockets if you try to accelerate this fast, and there might be better ways to reach this velocity. An old school method of starting large synchronous motors is, believe it or not, to use other motors or mechanical means like a gas-powered engine to accelerate an unloaded rotor to near synchronous speeds before turning on the exciter. Once locked into the synchronous speed, the motor can then be put to work. A more modern method might to use a variable frequency drive or motor drive to slowly ramp up excitation frequency on the stator so the rotor is afforded a gentle means of acceleration. You often find this method employed with permanent magnet synchronous motors, since the rotor field isn't capable of being de-energized nor varied. Finally, smaller electrically excited synchronous motors can often be operated as induction motors or asynchronous motors during the starting stage to accelerate the rotor to near synchronous speeds before turning on the exciter. Once locked into the synchronous speed, the motor can then be put to work. This does necessitate some modification of the rotor, in that in addition to the field coil reserved for synchronous operation, the rotor also needs to include a cage-like structure characteristic of an induction motor for the starting phase. These are sometimes called amortisseur or dampening windings. Bonus points if you can pronounce amortisseur properly, as I've yet to do so myself. In summary, the desirable constant speed characteristics of synchronous motors come at a price of slightly more complicated means of construction, starting, and protection. Let's examine the other half of the three-phase AC motor branch, induction motors. Induction motors also use a rotating magnetic field in the stator that for all intents and purposes is identical to that employed by the synchronous motors. Induction motors, however, establish an electromagnet on the rotor using different means. Obviously, the means of doing so is via induction. Induction is a fancy term used to describe a magnetic, not physical link between two circuits. You'll recall we examined inductors and transformers in previous lectures at the Big Bad Tech channel. There are two common types of three-phase AC induction motors: squirrel cage induction motors and wound rotor induction motors. Squirrel cage induction motors are probably the most popular industrial motor in the known universe simply because they're easy and inexpensive to build, relatively efficient, and don't require much maintenance. When I say the word motor, most likely I'm talking about a squirrel cage induction motor unless specifically stated otherwise. All your initial efforts at understanding motors needs to be invested in understanding this motor because this is the motor you will most likely work on. Induction motor rotors can be visualized as a hamster wheel style cage. A traditional squirrel cage induction motor features a cast aluminum or copper cage, whereas a wound rotor induction motor, as the name implies, features wire wound coils that create the cage. Beyond this basic construction difference, the wound rotor induction motor also features electrical connections to the rotor via a series of slip rings. You note the schematic symbol for the two types of induction motors both feature three-phase AC connections to the stator. A squirrel cage induction motor does not have connections to the rotor, whereas a wound rotor induction motor does. I'll explain the purpose of the wound rotor induction motor rotor connections in a moment. The operational principle of induction motors isn't that easy to understand, especially when you're trying to do a brief overview and use crappy diagrams like I am. However, here's my best take. We'll examine Faraday's law of induction in greater detail in later lectures. However, as a summary of the process, a voltage differential is created across the terminals of a coil proportional to the rate of change of magnetism and the number of coils in the changing magnetic field. Faraday's law of induction applied to induction motors means current flowing in the stator windings creates a rotating magnetic field. The rotor experiences a changing magnetic field, and via induction, a voltage differential occurs and thus current flows on the rotor. Consequently, the induced current flowing in the rotor creates its own magnetic field on the rotor, which then interacts with the stator rotating magnetic field such that the rotor is twisted or dragged along with it. Key to this interaction between magnetism, electricity, and movement is the important qualifier, changing magnetism. Induction doesn't happen if the magnetic field isn't changing. This means the stator rotating magnetic field needs to regularly sweep through and overlap the conductive bars in the rotor. This observation explains an important property of all induction-style motors. That property being, induction motors do not rotate at synchronous speed, but rather lag behind synchronous speed, even in the unloaded state. I say again, induction motors do not rotate at synchronous speed, but rather lag behind synchronous speed, even in the unloaded state. To put it another way, the stator rotating magnetic field is always ever so slightly faster than the rotor, such that the stator rotating magnetic field regularly catches up with and overlaps the rotor. The degree of differential between the rotor and synchronous speed is sometimes called slip, where slip is calculated as the rotor speed minus the synchronous speed over the synchronous speed times 100%. The behavior of induction motors can be summarized quite compactly on something known as a speed-torque curve, where torque is on the vertical y-axis and speed is on the horizontal x-axis. Consider one such plot of a Design B squirrel cage induction motor, a common multi-purpose motor. One can also plot mechanical power output at various rotational speeds, where you'll recall that mechanical power can be calculated as torque times rotational speed divided by the constant 9.55. There are several points of interest on these graphs. 1. The synchronous speed. This is the speed of the stator rotating magnetic field. You'll note everything on the speed-torque curve and power curve is less than the synchronous speed, because induction motors must by necessity slightly lag the synchronous speed, even in the unloaded condition. 2. The no-load speed. This is the free spinning speed of the rotor when it exerts no torque. In the no-load condition, the motor is spinning respectively fast, but it isn't doing anything. This is an occasion of 0 watts of mechanical power output and a small percentage of slip. 3. The rated speed. This is the speed of the rotor when it exerts the rated torque and produces the rated power. This is the data you would see on a motor nameplate because it's normally the most efficient means of operating this particular motor, or nearly so. Anything to the right of the rated condition is an underloaded condition, and theoretically, the motor can operate indefinitely at or under the rated condition. In contrast, anything to the left of the rated condition is an overload condition and isn't meant to be sustained for any length of time. Motors are customarily operated at or near the rated condition. Given the rotor increasingly lags the synchronous speed, this is an occasion of increased slip. 4. The maximum power point. This is where the speed and torque form a maximum power product. It's normally not the most efficient operating point, but the motor can temporarily operate above its rated condition. This is also an occasion of increased slip. 5. The breakdown or maximum torque condition. This is the maximum torque capable of being produced by the motor. Beyond this region, as the name implies, output suffers. This is also an occasion of increased slip. And finally, 6. The locked rotor condition. This is the torque exerted by the rotor at standstill. In the locked rotor condition, the motor exerts a respectable amount of torque, but it isn't going anywhere. This is an occasion of 0 watts of mechanical power output and maximum slip. If you were to concentrate on the far right side of the speed, torque, and power curves at and around the rated conditions, the plots should make intuitive sense. Load an induction motor up and it'll slow down. Unload the motor and it'll speed up. I know it's not really linear, and there's a clear roll-off as the motor approaches breakdown torque and maximum power, but if you squint your eyes just right, at or around the rated conditions, performance is relatively linear. In addition to experiencing peak efficiency in this region, it's largely for this reason motors are ideally operated at or near the rated condition. Load the motor up, it'll slow down. Unload the motor, it'll speed up. I should mention the speed torque curve and mechanical power chart are meant to represent a general purpose design B squirrel cage induction motor. Other speed torque profiles exist, the second most common being a NEMA Design D motor. Design D motors are designed for high inertia starts like a crane or a hoist. As evidenced by their speed torque curve, Design D motors produce high torque at low speeds. These curves imply that a Design B motor peak mechanical power output, the product of torque and rotational speed, occurs at a faster rotational speed and less slip, whereas a similarly rated Design D motor peak mechanical power output occurs at a slower rotational speed and a slightly higher slip. You note the B power curve is a more significant rightward lean, the D power curve not as much. This again points towards the intended purposes of these different types of motors. Type Ds are designed to favor the low speed, higher slip, higher torque applications one would expect for high inertia loads. The fundamental differences between Bs and Ds is their motor design. Design D squirrel cage induction motors, in comparison to Design B squirrel cage induction motors, feature conductive bars in the rotor with higher resistance. Which leads us right into a discussion on wound rotor induction motors. Squirrel cage induction motors, despite their simplicity, aren't easy to manufacture above a certain size. For this reason, rather than casting the rotors, wound rotor induction motors, as the name implies, use wire-wound coils on the rotor. This substantially simplifies construction for larger motors and yields an unexpected benefit. One now has access to the rotor via the slip rings. Wound rotor induction motor includes slip rings that maintain connection to the rotor windings regardless of the orientation of the rotor. When the windings are short-circuited, the wound rotor induction motor behaves just like a low-resistance rotor design B squirrel cage induction motor. If, however, the wound rotor induction motor needs to yank a load with a substantial static inertia to a start, one can add external resistors to the rotor such that the wound rotor induction motor behaves just like a high-resistance rotor design D squirrel cage induction motor. One can additionally vary the amount of resistance to indirectly control speed at various torque conditions. You used to see this method back in the day before motor drives, but only on rare occasions would you see this today. Now, motor drives make the direct control of excitation frequency a more efficient means of speed control than does varying rotor resistance of wound rotor induction motors. We'll examine motor drives and wound rotor induction motors in greater detail in later lectures. The other side of the motor family tree features several different configurations of DC motors. You'll recall DC motors consist of two basic parts, the field, i.e. the stationary part, and the armature, i.e. the rotating part. The primary difference between the different classes of DC motors is the electrical relationship of field and armature. You may encounter permanent magnet DC motors, separately excited DC motors, shunt wound DC motors, series DC motors, two types of compound DC motors, and the increasingly popular brushless DC motor. A permanent magnet DC motor features a permanent magnet on the field and an electrically excited armature winding. A separately excited DC motor features an electrically excited field winding as well as an electrically excited armature winding driven by two independent electrically isolated voltage sources. This configuration offers a degree of flexibility, however it necessitates two sources and a more complicated means of control. A shunt wound DC motor features an electrically excited field winding and an electrically excited armature winding wired in parallel with one another, driven by a single DC voltage source. In contrast, a series wound DC motor features an electrically excited field and armature windings wired in series with one another, driven by a single DC voltage source. Series wound DC motors are known for their high starting torque and are normally employed in applications requiring the movement of a heavy load with a degree of static inertia. Compound wound DC motors are combinations of shunt and series wound DC motors. A long shunt compound DC motor features a shunt field winding in parallel with an additional field winding in series with the armature. In contrast, a short shunt compound DC motor features a shunt field winding directly in parallel with the armature and an additional field winding in series with a parallel pair. Customarily, the series and shunt winding in compound DC motors are wound such that they mutually reinforce one another. Such compound DC motors are known as cumulative compound DC motors. There also exist differential style compound DC motors, ones that the series and shunt windings oppose one another. You'll most likely not encounter differential compound DC motors, and I have no plans to discuss them in further detail in the future. All these types of DC motors operate similarly and necessitate a brushed connection to the armature via a device called a commutator, which we'll examine shortly. Lastly, the brushless DC motor is the opposite of a permanent magnet DC motor and features an electrically excited field winding or windings and a permanent magnet armature. As implied by the title, a brushless DC motor necessitates no brush connection to the armature, nor does it necessitate a commutator. In fact, since the brushless DC motor is so different than the other DC motors, let's just omit it for now and reintroduce it after we discuss traditional DC motors. All these types of traditional DC motor configurations produce different speed and torque profiles and inherent advantages and disadvantages, which we'll discuss in greater detail in later lectures. Today's discussion is intended to be introductory in nature. Let's briefly discuss the mechanics of traditional DC motor operation. Because DC supply voltage is of fixed polarity and does not cyclically oscillate like an AC source, most DC motors are not powered by a rotating magnetic field in the traditional sense, but rather a continuously misaligned magnetic field moving to seek alignment. DC motor armatures actually consist of several different windings, only a portion of which are electrically excited at any given time. Connection to these various sections of the armature is made and broken via something known as a commutator. Upon first inspection, a commutator might look like a slip ring, but it most assuredly is not a slip ring. You recall the slip rings found on synchronous and wound rotor induction motor rotors were continuously conductive rings that maintain electrical contact between a stationary connection and rotating rotor winding regardless of rotational position. A commutator is plainly divided and includes conductive and non-conductive sections such that only selective portions of the armature windings are energized at any particular time depending upon rotational position. DC electricity is routed through the armature winding of choice via a pair of brushes. As the armature rotates, the commutator breaks one connection and establishes another. As a simplification, consider the rotating armature with three windings, green, orange, and purple, inside a fixed magnetic field. The stationary field could be a permanent magnet or separate shunt, series, or cumulative compound wound electrically excited in nature. We don't care. Long story short, the nature of the field windings largely doesn't matter. All it does is establish a fixed magnetic field, in this case, north to south, left to right. Via the brush connection to the commutator, DC electricity travels through the various sections of the armature. Let's say in this first rotational position, current travels through the green winding G to G prime, such that an armature magnetic field is established north to south, top to bottom. The remaining orange and purple windings of the armature are de-energized in this rotational position. As you are no doubt aware, opposite magnetic polarities attract, and like magnetic polarities repel. The field south pole repels the green armature winding south pole and attracts the green armature winding north pole. Similarly, the field north pole repels the green armature winding north pole and attracts the green armature winding south pole. As a result, the freely moving armature and everything attached to it rotates clockwise towards alignment. Just before the green armature winding reaches full alignment, the commutator breaks connection to the green winding. Immediately following this, it establishes connection with the orange winding O to O prime. The remaining purple and green windings of the armature are de-energized in this rotational position. As previously, the fixed field south pole repels the orange armature winding south pole and attracts the orange armature winding north pole. Similarly, the field north pole repels the orange armature winding north pole and attracts the orange armature winding south pole. As a result, the freely moving armature and everything attached to it rotates clockwise towards alignment. Just before the orange armature winding reaches full alignment, the commutator again breaks connection to the orange winding. Immediately following this, it establishes connection with the purple winding, P to P prime. The remaining green and orange windings of the armature are de-energized in this rotational position. As previously, the field south pole repels the purple armature winding south pole and attracts the purple armature winding north pole. Similarly, the field north pole repels the purple armature winding north pole and attracts the purple armature winding south pole. As a result, the freely moving armature and everything attached with it rotates clockwise towards alignment. Just before the purple armature winding reaches full alignment, the commutator again breaks connection to the purple winding. We've turned 180 degrees. The rest of the cycle just repeats itself. Energize G prime to G. Turn. de-energize. Energize O prime to O, turn, de-energize. Energize P prime to P, turn, de-energize, to go right back where we started, having accomplished a 360-degree turn. The process again repeats itself in a continuous cycle. If you think about it, the armature is like that hopeless dope Charlie Brown forever getting tricked into kicking a football only to have it pulled away at the last moment. Every time the armature moves towards alignment, just before it gets there, the commutator breaks connection and resets the playing field. As a result, the DC motor continuously rotates, seeking alignment. It's never going to get there, but it thinks so. More robust DC motors include more windings in the armature, such that the torque isn't pulsed or jerky. As with slip rings, the brush and the commutator itself are subject to mechanical wear or routine maintenance, and may necessitate period inspection and replacement. Additionally, since the commutator, unlike a slip ring, repeatedly makes and breaks connection, brushes may experience sparking due to inductively generated voltage spikes. For this reason, you may encounter DC motors with additional accessory windings, sometimes known as interpoles, to cancel out these effects. Additionally, we'll learn in later lectures that the armature and field winding magnetic fields aren't really two independent magnetic fields, but rather coalesce into one single magnetic field, and sometimes this interaction, called the armature reaction, distorts or shifts the plane of rotation. For this reason, certain types of DC motors may also include other auxiliary compensating windings to cancel out these effects, or may feature a movable brush rigging that allows the technician to establish a proper relation between the neutral plane of the motor in operation and brush neutral such that minimum sparking occurs. Lastly, DC motors are easily reversible by interchanging the polarity of the armature or field winding, but not both. Customarily, one swaps out the armature polarity. For example, consider a shunt-wound DC motor that rotates clockwise when DC polarity is applied positive to negative, F1 to F2, and A1 to A2. If, however, we apply DC polarity positive to negative, F1 to F2, and A2 to A1, we would witness the motor turn counterclockwise. Now that we've got an idea of how traditional DC motors operate, let's reintroduce the brushless DC motor. A brushless DC motor is essentially the opposite of a permanent magnet DC motor and features an electrically excited field winding and a permanent magnet armature. In a weird sort of way, wrapping back to one of our earlier motors we discussed, the brushless DC motor has far more in common with a permanent magnet synchronous motor than it does traditional DC motors. You can think of it as convergent evolution. It's still lumped into the DC motor family because it is intended to operate using fixed polarity DC. Like a permanent magnet synchronous motor, a brushless DC motor features a permanent magnet armature, thus freeing it from the necessity of brushes and a commutator. Rather than mechanically commutating the armature connection, a brushless DC motor electrically commutates connection to a series of field windings via integrated power electronics devices known as transistors. Consider this extremely simplified example of a brushless DC motor featuring 3 independent isolated field windings radially distributed at 120 degrees around the armature. When field winding 1 is electrically excited by DC energy, it establishes an electromagnet which attracts the permanent magnet armature. Similarly, when field winding 2 is electrically excited by DC energy, it establishes an electromagnet which attracts the permanent magnet armature. Finally, when the field winding 3 is electrically excited by DC energy, it establishes an electromagnet which attracts the permanent magnet armature. Successive time pulses to the field windings 1, 2, 3, 1, 2, 3 essentially creates a rotating magnetic field, as would a 3-phase AC permanent magnet synchronous motor, only a brushless DC motor does so using DC. Brushless DC motors, despite the initially higher expense for the integrated power electronics devices, are known to be relatively maintenance-free. Unlike a traditional DC motor, where one swaps the polarity of the armature or the field winding to reverse direction, a brushless DC motor reverses direction by swapping the sequence of pulsed DC voltages applied to individual field windings. If the sequence 1, 2, 3 initiates counterclockwise rotation, the sequence 2, 1, 3 would initiate clockwise rotation. Alright, now that we've discussed the 2 most important branches of the motor family tree, let's look at the third particularly stunted branch, known as single-phase AC motors. Everyone has relatives they're not proud of. You know, the crazy cat aunt, the uncle that can't be within 1,000 feet of a school or a park frequented by children, and all those fairy wing wearing hippy-dippy or perpetually pissed off paranoid gun nut cousins you'd rather not have at the Turkey Day table. Single-phase AC motors, that's them. They're the malformed mutant cretins locked in the basement of the motor family tree that I do not want to talk about. Like their more dignified industrial 3-phase AC cousins, most single-phase AC motors use a rotating magnetic field However, to do so with a single phase requires contrived methods bordering on the hokey and unbecoming. This being said, if single phase AC is all you got, a single phase AC motor will get the job done and produce rotating mechanical power output just like the rest of the motor family tree. There are numerous types of single phase AC motors, and most likely I'll cover only the most popular types, being the split phase, capacitor start, capacitor run, and maybe the shaded pole and repulsion start induction run motor if I've got time. Straddling the no man's land between single phase AC motors and DC motors is the universal motor. As the name implies, a universal motor can run on DC or single phase AC. However, just like cutting a fish in half and sewing it to half a monkey, it doesn't swim well, nor does it climb trees well, but it does both swim and climb trees to a certain extent. Universal motor is really just a series DC motor. Think commutator and brushes, with compensating windings on the field windings designed to minimize inductive losses when run on AC. There you have it. In summary, the motor family tree has three main branches: industrial three-phase AC motors, DC motors, and single-phase AC motors, with the universal motor straddling the single-phase AC and DC motor split. Inside the industrial three-phase AC branch, there are two sub-branches: synchronous and induction motors. Both these types of industrial three-phase AC motors make use of a rotating magnetic field in the stator. The rotors of synchronous motors are synchronized or follow the synchronous speed, whereas rotors of induction motors lag the synchronous speed, even in the unloaded state. For this reason, induction motors are sometimes called asynchronous motors. Each of these subbranches has two more subbranches. Inside the synchronous motor subbranch, you might find electrically excited synchronous motors and permanent magnet synchronous motors. Inside the induction motor subbranch, you might find squirrel cage induction motors and wound rotor induction motors. The DC motor branch is a couple different styles of traditional DC motors, featuring a brush connection to the armature via commutator. Notably permanent magnet DC motors, separately excited DC motors, shunt wound DC motors, series DC motors, and two types of compound DC motors. The DC motor branch also includes the brushless DC motor, which lacks a mechanical commutator, but rather electrically commutates the field windings via integrated power electronics devices such that it acts similarly to the permanent magnet synchronous motor. Lastly, the single-phase AC motor branch features a number of insignificant play toys. But wait, that can't be it, can it? No. Like I told you earlier, there are a lot more types of motors out there, and one can add numerous branches, sub-branches, stems, twigs, buds, knotholes, birds, squirrels, and raccoons' nests, leaves, and nuts to this tree as you wish, but when you get right down to it, these are the important parts of the tree that you can make lumber out of. The rest is just toothpicks. We'll examine some subtle and not so subtle variations on these themes in later lectures. Finally, the curious among you may be wondering where servo motors fit into this picture. At risk of igniting a forest fire of rage, I will be so bold to proclaim this fact: there is no such thing as a servo motor. I say again, servo motors do not exist. There are, however, servo systems, of which one component might be a motor, and some motors might make better components for servo systems than others. Allow me to explain. A servo system consists of an actuator, a sensor, and a controller. The actuator is something that converts incoming primary power to some form of usable mechanical power output. A hydraulic servo system might use a linearly actuating hydraulic cylinder as an actuator, whereas a motor servo system would use a rotating motor as the actuator. The idea of a servo system is to control the output of the actuator such that force, speed, position, or some other measurable property influenced by the actuator is kept inside a specific range defined by the controller. The controller requires two basic inputs. One, some desired set point established by an operator. In the case of a servo motor system, it might be some desirable torque, rotational speed, or maybe rotational position. And two, the controller requires a means of monitoring the actual output of the system. A dynamometer in the case of torque, a rotational speed sensor in the case of rotational speed, or an encoder in the case of rotational position. The controller then continually compares the desired set point with the actual output of the system via a feedback loop. If there's a difference between the desired set point and actual output, there's an error, and the polarity and magnitude of this error represents by how much the system must increase or decrease its output to achieve the desired set point. Long story short, servo systems rely on sensors and feedback to produce some desired effect. For example, consider a servo system that necessitates a motor ramp speed up to 1800 RPM and keep it there. This system might include a motor drive, a motor, and a rotational speed sensor. A controller might be integrated into the motor drive, or maybe some external device like a programmable logic controller, or PLC. Upon start, the motor drive steadily increases excitation frequency over a specified time period until the motor is turning at the specified 1800 RPM. The desired output is 1800 RPM. The actual output is 1800 RPM. The error is 0 RPM, and motor drive continues to supply the same excitation frequency sufficient to drive the motor at 1800 RPM. If, however, the motor shaft experiences oppositional torque such that the rotational speed now drops to 1700 RPM, via the feedback loop, the controller realizes the actual output is 100 RPM lower than the set point, and it must increase excitation frequency. The motor drive ramps up excitation frequency ever so slightly until the error between the desired set point and actual measured output is again 0 RPM. In this operational state, if the oppositional torque was removed, we might expect the output speed to overshoot the desired 1800 RPM. Lacking opposition, let's say the motor speed jumps up to 1900 RPM. Via the feedback loop, the controller realizes the actual output is 100 RPM higher than the set point, and it must decrease excitation frequency. The motor drive ramps down excitation frequency ever so slightly to the error between the desired set point and the actual measured output is again 0 RPM. Does all this monitoring, adjustment, and correction happen instantly in a servo system? No. There is some measurable rise and fall time and over and undershoot. However, a properly turned servo system should ideally maintain output inside a given range. Yes, there is a motor in this system, and yes, people do refer to these motors as servo motors, but they are technically not correct because there is no such thing as a servo motor in isolation, but rather a motor must be part of a larger servo system, which includes an actuator, which may be a motor, a controller, and a sensor and a feedback loop to make it all work as it should. This is, of course, neglecting sensorless vector control, which, as they say, is another barrel of rage-infected monkeys, which we'll crack open at a much, much later date and time. Speaking of rage-infected monkeys, I should probably discuss stepper motors while we're here. A stepper motor is another type of special-purpose motor system that drives a motor shaft in stepped, hence the name, or pulsed increments to various predefined positions. Stepper motors are used for precise position control. You might find them on CNC mills, lathes, and routers, or 3D printers. Most, but not all, stepper motors are DC-style motors. Upon receipt of a single pulse, the stepper motor controller would move the shaft from one defined position to another. Stepper motors with higher resolution are capable of moving smaller and more accurate steps. We'll examine stepper and servo systems in later lectures. Finally, I should probably mention that not all motors feature an external stator wrapped around an internal rotor. And believe it or not, some designs include an external rotor wrapped around an internal stator. Matter of fact, as an extreme example of the variances in construction difference you may encounter, consider a linear motor that unrolls the stator in a linear fashion called a platen, and the rotor, called the reaction plate, slides linearly along it. It still uses motor theory, however it moves linearly rather than rotationally. Does it match my earlier definition of a motor? Not really, but it's definitely not a solenoid. Finally, I do want to remind you that motors are just one aspect of what could rightly be considered an electrical machine, where an electrical machine can be a motor or a generator. As an extreme example of this duality, consider a rotary phase converter, which is a method of creating three-phase AC power from single-phase AC using an unloaded three-phase AC motor, often called an idler motor, driven by single-phase AC. I know this sounds confusing, but it's a simplification of this process. You could think of this as a generator consuming single-phase AC to produce mechanical power output. This mechanical power output is then consumed by a three-phase AC generator to produce three-phase AC. We'll examine the generator aspects of electrical machines in later lectures. Alright, that is about it. In conclusion, this lecture accomplished a brief tour of the motor family tree, and along the way we learned to recognize identifiable traits that distinguish one motor from another. Additionally, we introduced basic concepts in turn to assist you in classifying motors when encountered in their natural habitat. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.